Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over calorimetry. We're going to solve this problem by using specific heat and calorimetry. So let's get into this. So the problem starts out, care must be taken in preparing solutions of solutes that liberate heat on dissolving. The heat of solution of NaOH, sodium hydroxide, is negative 42 kilojoules per mole of NaOH. To what approximate temperature will a sample of water, originally at 21 degrees Celsius, be raised in the preparation of 500 milliliters of 7.0 molar NaOH? Assume that the specific heat of the 7.0 molar NaOH is the same as the specific heat of water. So let's get into this. So first thing we want to do is figure out the number of moles that we are of NaOH we are creating, because we're told that negative 42 kilojoules per mole is given off of the NaOH, per mole of the NaOH. So if we first calculate the number of moles of NaOH that is being produced in the formation or the preparation of this 500 mil sample, or this 500 mil amount of 7.0 molar NaOH, then we can then use that to find the heat that's evolved from making that amount of NaOH. Because again, this is negative 42 kilojoules of energy released per mole of NaOH formed. So we need to figure out how many moles of NaOH is formed. And also pay attention, this is negative. This is a exothermic reaction. The negative means that heat is being lost by the reaction, meaning heat is released, given off to the environment. So that's a negative sign. Okay, so that's what this negative sign means. Okay, so let's figure out how many moles of NaOH is formed. So let's start with the 500 milliliters of the NaOH solution over 1. We're starting with 500 milliliters. We're starting with milliliters because everything else that we're given can be used as a conversion factor. For example, molarity is moles per liter of the NaOH. So the number of moles, 7 moles, 7.0 moles of NaOH per 1 liter of the NaOH solution. So I can use that as conversion to convert from liters to moles, which is what I want. But I need to convert this first to liters. So let's do that. Okay, so I know that 1 milliliter is equal to 1/1000th of a liter. That's what milli means. Milli means 1/1000th of. So I'm going to put 1 milliliter of NaOH solution on the bottom. And I'm going to put 10 to the negative 3 for 1/1000th liters of the NaOH solution on top. So milliliters of the NaOH solution cancel out. Now I have liters. Now I can use the molarity. So now I have 7.0 moles of NaOH per liter of the NaOH solution. So I'm going to put 1 liter of the NaOH solution on the bottom and 7.0 moles of NaOH on top. So the liters cancel out. Now I have moles. So when I multiply and divide, I get 3.5 moles of NaOH formed. Okay, great. Next step is I'm going to use this negative 42 kilojoules per mole of NaOH as a conversion factor. So this is telling me that for every mole of NaOH formed, I get negative 42 kilojoules of energy, right? So now I'm going to start with the 3.5 moles of NaOH. Now, I could have, instead of stopping here and then calculating this, I could have just went straight to the kilojoules because since I have moles of NaOH, I can use this as a conversion factor, put the mole, 1 mole of NaOH on the bottom. So here, let me show you what I mean. I could have just did this, right? And then I would put 1 mole of NaOH on the bottom, and then that would be a negative. I would put negative 42 kilojoules of energy on top. And also because I'm going to be using Q equals MCAT, and I got to use the specific heat of water. The specific heat of water has joules, so I'm going to want to convert this to joules. So then I could just convert kilojoules to joules. So 1 kilojoule of energy is equal to 1,000 or 10 to the third joules of energy. Kilojoules would cancel out, moles would cancel out, and then I would get the amount of joules that I am looking for as well. So then all I would need to do is multiply across the top, divide by the bottom, and I would get my answer. And that answer would be negative 147. So this would be negative, I'll write down here, negative, excuse me, 147,000 joules, right? I could just do it in one full step, right? Or, like what I was about to do, I stopped it here and I found the moles of NaOH, and then I could just take the moles of NaOH and then continue these steps here, right? So here again, 1 mole of NaOH, NaOH on the top, negative 42 kilojoules, negative 42 kilojoules on the top, and so on. Then I could do the joules multiplied by 10 to the third joules over 1 kilojoule. So these would cancel out, and I would end up getting the same answer, 147,000 joules, right? So whichever way works is whatever works for you is whatever works, right? Either way is fine. You can do it in 2 steps, or you could just do it in 1 full step. You should get the same answer. Okay, so now that we've got the amount of heat, so this is the amount of heat in joules that's been liberated or released by the formation of 3.5 moles of NaOH, right? So that means, and what we're trying to find is what's the temperature change of the water, right? So this reaction is taking place in water. So got to remember that the heat lost, right? So the heat of the reaction is going to be equal to the negative of the heat gained by the water, right? Or you could put the negative on this side. So we're losing energy here. So the amount of energy of the water, the heat absorbed by the water, is going to be equal to the negative of the heat released by the reaction. So if you remember that, then you know that the water is absorbing heat, and then so this is going to be positive. So remember, if you're losing heat, the change in energy, the Q value is going to be negative. So the Q, the heat of the dissolving of the solution here, is this amount here, right? So this is lost by the reaction. This is lost by the dissolving of the NaOH. So this is exothermic. It's negative. It's lost. The water that the reaction or the dissolving is taking place in is absorbing that heat. We're assuming that it's going to be a complete absorption, absolute no lost heat. So all the water is going to absorb all that heat that's released, so it's gaining the heat, so it's positive. So you would just change the sign, right? Which is what this means. So if I plug in this value here, negative minus 147,000 joules of energy is equal to Q of H2O. Negative and negative becomes positive, so this becomes 147,000 joules of heat picked up by the water. Okay, so what do we need to find? We need to find the temperature change of the water. So we're going to have to use Q equals MCAT. So if you remember, Q, in this case, we're looking at the Q of the water is equal to the mass of the water multiplied by the specific heat of the water multiplied by delta T of the water. Okay, mass of the water. Well, Q, we already found Q, right? So that's going to be a positive 147,000 joules. What about the mass of the water? Well, we're not given any information about the mass of the water. We are given the milliliters of the solution of NaOH, right? But we're not given the mass. If we were given the density of the NaOH solution, then we could assume that it's a 1-to-1 because the density of water is, well, let me step back. So if we were given the density of the solution, we could then use density to convert the milliliters to grams. But they didn't give us the density of the solution. But they did tell us that the specific heat of the solution is the same as the specific heat of the water. So it's safe to say that we can assume that the density of the solution is going to be the density of water, right? So if the density of water is 1 gram per 1 milliliter, and if we assume this has the same density of water, then same thing here. So that means for every milliliter of the solution, it's going to be 1 gram of the solution. So it's 500 grams. So that's going to be equal to 500 grams of the solution multiplied by the specific heat, which we were told is going to be the same as the specific heat of water, which is going to be 4.18. Let me double check. We're going to use 4.186, 4.186 joules per gram degrees Celsius, and then the temperature change. But we also have to remember that temperature change, right? Where can I write? Temperature change is going to be equal to the final temperature minus the initial temperature. So we could substitute this in for this. So it's going to be final minus initial. And we don't know the final. We're being asked for the final. To what temperature will the sample of water be raised? So that would be the final temperature. We're given the initial temperature, which is originally at 21 degrees Celsius. So we got final TF minus the initial, which is 21 degrees Celsius. And so now that I have everything here, we're going to multiply these together. So it's going to be 147,000 joules is equal, these two multiplied together is going to be 2093. So that's going to be 2093. And notice grams are going to cancel out. So that's going to be joules over degrees Celsius that's left. And then we're going to multiply these here. Oh, I'm sorry. And then this is going to be multiplied by TF minus 21 degrees Celsius. So now I can take this and multiply it. I'm going to distribute it through to these two. I'm going to multiply this to this and this to this. So again, that's going to be 147,000 47,000 joules is equal to this times this, which is going to be 2093 joules over degrees Celsius multiplied by TF, the final temperature. And then this times this is going to be giving me a negative. But notice that the degrees Celsius here and the degrees Celsius here are going to cancel out. So that's going to be a negative. What's that answer? 43,953. 43,953. So 43,953 joules of energy. Okay, so now I have this simplified here. I want to get joules with joules, so I'm going to add 43,953 joules over here. I'm going to add 43,953 joules over here. This is negative and positive are going to cancel out. Add these together, and I get what do I get? I get, let me look here. Sorry, that's 199.53. So add these together, I get 190,953 joules. So this many joules is now equal to 2093 joules over degrees Celsius multiplied by TF. So now to find the final temperature, all I have to do is divide both sides. So I'm going to divide both sides by 2093 joules over degrees Celsius. Divide this by 2093 joules per degree Celsius. And the joules are going to cancel out. And I'm left with degrees Celsius, which is what I want for my TF, for my final temperature. Temperature is measured in degrees Celsius. And when I calculate that, I get TF is equal to 91.2 degrees Celsius. Let me double check that. 91.2, that is correct. That is what I got. So, ladies and gentlemen, that is how you can use calorimetry and to find the missing link or whatever. In this case, we were asked to find the final temperature. And I hope this was helpful. If this helped you out, if you like this video, then please, by all means, like the video, share the video, hit that like button over here somewhere. Also, do me a favor, hit that notification bell, subscribe to the channel. That would help me out a lot. When you hit the notification bell, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or a topic you want me to cover, put that down below. I would love to do that. Thank you for joining me, and have a great day.